So we're on chapter 15 of your chemistry book. We're going to be talking about acids, bases, and salts. So what does this have to do with our world? A lot. Especially you see here a picture of the ocean here and how much salt the ocean produces. And how does it produce this salt? Well, producing salt has a lot to do with the combination of acids and bases in water. And to find out which acid and which base as they react together, and which salt, because there's many different kinds of salts, and there's many different kinds of acid and bases, and they're common in our world that we live in. Probably you can find multiples in your house. Not only that, there's acid and base reactions going on in your body. So we're going to be talking about what equivalent is, what normality is, an ion product constant of water here. We're going to talk about a pH and logarithm, pH and pOH, and we'll be talking about this in this chapter. I'll find out some of the things about acid, bases, and salts. So almost everyone has some picture or idea which comes to mind when you say acid, base, and salt, and much attention is given to acid rain. Various advertisers promote their products saying they're non-alkaline or the low pH or acid balanced or onto low acids, low salts in your diet. Many compounds in our society are acid, bases, and salts. And many fruits, like certain citric fruits are acidic. When we think of vinegar is called acetic acid. And apples are called malic acid, and grapes are called tartaric acid, and gastric juices, hydrochloric acid in our stomach, breaking down food products. Very important thing in our stomach that hydrochloric acid does. Salts, there's a wide range of salts and a lot of different ionic compounds that make different kinds of salts. Things like sulfuric acid and phosphoric acid and nitric acid combining to make these salts. Also, a lot of different household cleaning things like drain cleaners have are bases, and other bases are like antacids. When you take your Alka-Seltzer or you're taking any kind of antacid, it's basically going against the acid in your digestive tract, right? So we're going to need to know a lot about acid, bases, and salt. Isn't it wonder how God puts things together? Even in our blood system, there's a buffer system that has to do with keeping our pH with our acids and our bases at a certain level so that we could even live. And there's so many things going on in our body that have to do with acids and bases. So the nature of acids and bases. We're going to be talking about this Arrhenius concept. So Arrhenius seems like, where did you get that name? Well, Arrhenius came from a Swedish chemist, Svante Arrhenius, who lived clear back between 1859 to 1927. And he developed a theory in which he defined an acid as a substance that produces hydrogen ions when you dissolve it in water. And he defined base as a substance that produces hydroxide ions when dissolved in water. So make sure you remember hydrogen ions have a positive ion. Here's H, hydrogen with positive ion. And OH, hydroxide. Here's hydrogen oxide. Hydroxide have negative, and it is base. So he said when we have an acid, we're going to have a hydrogen. When we have a base, we're going to have hydroxide ions. So also these ions, I kind of skipped here, acids, when you dissolve them in water and you take some litmus dye, right? Here's a picture of it. Here's an acid, and you put a litmus paper in it. It will turn the litmus paper to red. Think of acid and red. They both end with a D, right? So acid, turns the litmus paper red. Now, if you have this litmus paper, and the opposite will happen with bases. So here's oven cleaner, which is really high base and of nitric hydroxide. So here we have this, and as it's changing here, it's going to change. Think of blue. Base turns to blue. So that's litmus paper. And also some other characteristics. You're going to be asked probably, what are the characteristics between acids and bases? So what do you think? Well, when you have acid and you taste it, it tastes very sour, right? And then also when you have an acid, it will react with certain metals, and like hydrogen gas will happen. So you have certain metals, especially zinc, and as you put them together, you'll get a lot of hydrogen gas from that. So you'll find that acids react with metals. Not all metals though. We'll see that later on. Also, the acid, of course, will change the litmus dye. What did we say? To red, from blue to red. Bases have this bitter taste, and they're very slippery, slippery feel. And they can neutralize acids, and they turn litmus paper, of course, we know, to from red to blue. So those are going to be probably on your test to know that. So let's go on. Here again, we have all these different things you can look in your cupboards, and you'll find like baking soda and lemon juice, and acids, vinegars, glass cleaners, heavy duty cleaners, and apples even. All these things, citrus, all these things in your cupboard all have to do with acids and bases. So let's go back one. There's one thing down here I didn't cover. Oh, okay. So when hydrogen gas is bubbled through the water, it reacts to produce hydrogen. So remember Arrhenius, it's always producing hydrogen. So when you have acid, it's going to react to produce hydrogen. And when you have a base, it's going to react to produce hydroxide. Here's an equation for hydroxide. Sodium hydroxide combined with water, and you get sodium and hydroxide. This is the equation for that. So it's a pretty simple equation, although we took the water was, in this equation you'd need water, but we have water there in the midst as the catalyst there. Water doesn't change in that point. So, and let's go back, just look at the acid one too. I don't think I went over. Here's the acid. When water reacts with, water is bubbled through the water, it reacts, an acid reacts. Here's hydrochloric acid. Going through the water, it changes, you get hydrogen and chloride, and chlorine, I should say. And hydrogen, chlorine, and chlorine are ions, and you'll get the hydrogen ion. That's what Arrhenius says causes it to be an acid. And again, OH causes it to be a base. So let's go on here. Okay, let's see. So now we're going to go on to, well, before that, this is another thing that's very important. Chemists usually assume that there's also a proton that exists as the hydrogen and water, and it's written and known as the hydronium ion. So we're going to be talking about this hydronium ion. Let's read this. It says, this concept, though adequate for some purposes, the Arrhenius concept, is limited to aqueous solutions. So Arrhenius, just we're looking at liquid aqueous type solutions. In addition, further study indicated that the simple proton does not alone exist in water. So it doesn't exist alone in water, but it's always hydrated. What's the word hydrated mean? Loosely bonded to water molecules. Hydrated is when you're full of water, or you're bonded to water, right? So chemists usually assume the proton to exist as hydrogen is written as H3O positive. See this here? H3O positive. And this ion is called the hydronium ion. So it's pretty important that you know the hydronium ion is this, because when you see this in the midst of chemistry, it's never going to be just a a lone hydrogen ion because it doesn't exist, so it always is put together with the water. So we have H3. Instead of H2O, you'll have H3O with a positive, saying basically there's an extra hydrogen there making it acid. So this is called the hydronium ion. So now we're going to go on to another concept, and it's another concept about acid and bases, and it happened later on in 1923. A Danish chemist named Johann Bronsted and English chemists got together, Thomas Lowry. Well, actually, they were independently. They got together after they both developed it, but they enlarged this definition. The definition of Arrhenius basically said it's going to produce hydrogen and hydroxide, ions. Well, now they thought this is more than that. This is more than this. It's going to actually be taking protons. So let's find out what the difference is. So the Bronsted-Lowry acid is a substance that can donate a proton to another substance. And the Bronsted-Lowry base is a substance that can accept a proton from another substance. Since water is not mentioned in these definitions, they can apply to many more situations than the definitions of the Arrhenius. So what is that saying? Basically, Arrhenius are saying you always have to have water. Well, not what the Bronsted-Lowry says. It doesn't need to have the combination doesn't need to have water all the time. So it's in fact, water is not even mentioned in the equation at all. So here's the reaction again. Here we have hydrochloric acid hydrochloride reacting, which is an acid, right? And it's reacting with a base, and it's going to produce the hydronium ion. Remember now, hydrogen, they're not saying hydrogen is all alone. It's going to be combined with oxygen here and chlorine. So basically the acid combining with the base is going to be producing, with this water, the base, actually the base being water in this situation, is going to produce the hydronium ion. So this hydronium ion, whenever you see this, that's going to be acid. That's an acid. So it says we see that hydrochloride is the acid, and it donates the proton to the hydronium ion here. So it's really taking this proton and giving it to this. See? And so in that way, the chlorine is going to be free, but this hydrogen is going to be going in. The water here is going to be taking that proton. So it's a transfer of that that proton in that sense. So let's look a little further. So it says Arrhenius definitions and Bronsted-Lowry definitions are similar, except Bronsted-Lowry definitions tell us more. So you can use Arrhenius more simple definition, or you can use the other, but the reverse is not really necessary. So, but when Bronsted-Lowry acids lose its proton, it forms what's called a conjugate base. And when Bronsted-Lowry base gains a proton, it forms a conjugate acid. So let's look at this 15.3 here. Here we have the acid forming here, 15.3. And as we look further, we'll have a situation here with ammonia. So here we have, this is what's called a conjugate. You're thinking, what is conjugate? Well, here we have, this is a base, so we have ammonium reacts with water according to this equation. So we have a base here. Here we have a conjugate pair because this base is reacting to form an acid. And so then the acid here on this side is forming a base too. One will be weaker than the other usually. The strong one will shift this to the weak. It's always going to be shifted to the weaker to make up the weaker to become equal, right? But you can look, these are the pairs right now they're talking about. You'll have a pair, a base and an acid pair on both sides, you see, as it reacts. So this is a Bronsted-Lowry was gaining a proton in this reaction. We have a conjugate acid of the base of water and chlorine in a conjugate base here. So just think of conjugate pair. Conjugate means it's producing something. It's producing something. So one side is producing the base to the acid and the acid to the base. So here's a picture there of a gas phase acid base reaction here. See, you see how in this case hydrogen is put into the water. So this is a gas phase. Here you have hydrochlorine gas and NaH onto producing. You have both of these here producing as they produce the gas, mixing with the gas. So crystals. So it happens not only in liquid but gas. But let's talk about this table here because you'll have to know probably something about this table. The acid-base definitions. So what we went over, this is kind of a review, but so Arrhenius says acid is a substance that produces protons that are hydrogen. Or it's a base if it produces hydroxide ions, which are OH. So we went over that. That's Arrhenius. So Bronsted-Lowry says basically this substance that donates a proton, and they're donating a proton, or a substance as a base that accepts a proton. And that's that proton represented hydrogen. So that's here where it's losing hydrogen or with their conjugate pair or vice versa, So the difference is the donating a proton or accepting a proton, or this is talking about the ions of hydrogen and hydroxide. But they're both doing same. You'll find it just depends on what concept you want to discuss, about acids and bases. So let's go on here. So water, it says in this, going over what is happening in what we just, in that equation that we just described, but we're saying in this reaction that water is an acid because it donates a proton. Water in some can act like an acid or basis depending on what way it is in the equation. So, but let's look, this is the important part right here. So, in this reaction, water and hydroxide are conjugate acid-base pairs. The other acid-base pair is going to be the ammonium pair, the ammonia. So the members of each, or this is nitrogen hydroxide, but the members of each acid pair differ only by a single proton, which is H proton. One is a reactant and the other is a product. So here we have, here in this picture, this figure here, you can see how this is a proton transfer reaction. So we have the acid, hydrochloric acid, and you have the base, which in this situation is going to be water. And so it'll form a conjugate base. See how it lost this proton here? And so it's a conjugate base. And as you go on here, you'll see it gained it over here. There's 1, 2 here, and there's 1, 2, 3. This is the hydronium molecule that always represents an acid, right? So here's the picture of it, how it looks. Same with the base. So we have the NH3 here producing as the base. You see 1, 2, 3, and the nitrogen and hydrogen here. These are 1 nitrogen and 3 hydrogen. And so here again we have the water, but you see the water now is acting like a acid instead. So the water here is going to lose, as it's losing, going to here, we'll have these two are forming the conjugate base. You see 1, 2, 3, and now it's going to be NH4. So the hydrogen is actually reacting now and has turned this around, this base, into an acid here. And then so we have the conjugate base being OH negative, which always makes it into a base. So now we have, this is producing a base in the midst of where this hydrogen proton is going, So here we have receiving the proton, donates the proton, the conjugate acid forming here, 1, 2, 3, 4, and onto the conjugate base. Just a picture of how the reaction looks when you have acid-base reaction. Example 15.1 here. Let's go over this because you might have one of these to do. So in each of the following, determine the Bronsted-Lowry acid and base and the conjugate base of these pairs. So let's see how to do this. So let's do this first one. This is HF, hydrogen fluoride, and we have OH, you know, and the OH meaning holding it as a base, you know, onto water and fluorine. So here, basically, you're freeing up this hydrogen fluoride with hydroxide, right? So here we have the acid. This is the acid. You know it's an acid because it's hydrogen fluoride is an acid. And then you know that this is base. OH is always the major base. So we have hydroxide there. So then we end up freeing the hydrogen here, and you can see how it produces fluorine and water. And these two are the conjugate pairs. These two and these two are pairs. You have the acid and the base and the acid. So you can see that the product has one less proton. So you can see how the conjugate bases and the product that has one more proton. So you can see the pairs. So these two pairs, you see, this is acid to base conjugate, and this is base to acid conjugate in the problem. So basically, that's what they wanted you to do, is to show you how to do that. The next one, this is B. The reactant hydrochlorine is converted to chlorine as a result of donating a proton to the reactant of NH3, which becomes this is the ammonia type reaction. The acid is thus HCl and its conjugate. Okay, let's look at this. You can read this as you read it, but to really understand it, let's look at the equation here. So here we have this is a hydrochloric acid, a very strong acid, and here we have the base NH3, and so here we have the conjugate pair here. These two, this first one here, you see the hydrogen is lost. So this turns into the conjugate base pair here. Conjugate base, and this would be the base here, as you see, turns into the conjugate acid here. It's gaining that hydrogen. So the one that gains when it gains a hydrogen, it's going to be the conjugate acid. When it loses, whoever loses, that's going to, it basically is going to be base, or as you lose it and gain it, you can see how that is either acid or base. So anyway, these two are the conjugate pair, and these two are the conjugate pair in that equation. So the next part is talking about how do we name. I always have a problem with naming them. I tend to name them wrong a lot, but it was really good to see how they want you to name them. And when you're dealing with chemistry, because if you're talking about an ide, you know, like a hydrochloride, or you know, or what makes us think it's, you know, ends in IDE, or you know, IC, or how do we do these? So there's two categories of acids. There's binary acids, and there's oxyacids, and both of these are named differently. So we're going to talk about naming. Binary acids are compounds of hydrogen and one other element. So we're talking about hydrogen, and they're generally non-metal. Sometimes they're semi-metals, but generally non-metals. So how do we name these? First, you're going to have a prefix, and the prefix being as you're naming these, the prefix is going to be, because they all have an H in front of them, that's hydrogen. The prefix is going to be hydro, from the word hydrogen. And then they're going to have a stem root, or the name of the non-metal, whatever metal that they're talking about, non-metal, I should say, whatever element they're talking about. You're going to put that next in the name. And then you're going to add IC And at the end, you're just going to put the word acid to tell everyone it's an acid. For example, a water solution, if you have hydrogen, bromine, then it would be hydro for hydrogen, bromic acid. They want the ic part, right? So onto an aqueous solution of hydrogen sulfide, sulfur here. Here's hydrogen and sulfur. It'd be hydro, meaning hydrogen, and sulfur. Sulfur is the non-metal here, sulfur, and it's going to end in ic, meaning acid, so it'll be hydrosulfuric acid. So here's some more up here in this list. Look at that list a little closer. So we have hydrogen fluoride. Here's hydrogen fluoride. And so it would end up naming this, it's going to be hydrogen fluoric acid. Here's hydrogen and chlorine. Hydrogen chloride here combining, we turn to hydrochloric acid. Hydrogen iodide, hydroiodic acid, hydroiodic acid. Onto hydrogen selenide, right here, hydrogen and selenide would turn to hydroselenic acid. See how they do it? So when I say hydrofluoric acid, hydrochloric acid, hydroiodonic acid, hydroselenic acid, see how they did? These are all binary that are compounds of hydrogen and just one other element. There's only one element in there. So that's one way. But also we have to name oxyacids. And these are called ternary acids, or they're a different kind. They're not just one as hydrogen with it. We'll see. They have oxygen in them. Let's just say they're called oxyacids, right? Or oxyacid onto ternary acids, but that's just another name. So, and these acids are based at polyatomic. Poly meaning many atom ions are put together to put this. For this, they want you to go back and review all of these different ions on the table. So when you're thinking of naming something, then you have to go back to that table to remember, okay, what was that? So, and I'm not going to go back to that table right now, but you'll know in going back to that table, you'll be able to find out. Well, let's go back to, what page was it on? Well, let's find out how we do this first. So the names of acids are formed from polyatomic ions ending in ATA. So if you have something that ends, and it's a polyatomic atom and it ends in ATA, then we're going to replace the ATA with the suffix ic, and then followed by the word acid. So the names of the acids formed from polyatomic ions ending in ITE. And they're going to be formed by replacing ITE with OUS. So now, instead of just ic, we have ic, IC, and OUS. So now we know that we're going to take, if we have ATA, at the end, we're going to turn it to ic. How can we remember that? I ate something and it turned icky. Ate ick, right? It's a good way to know it. And then the other is ite. That was an ite-os. Ite-os. I don't know how to do that, but O-U-S. Ite-O-U-S. Ite. But anyway, ate and ick are a good one to remember. I just have these different ways of remembering things. So here's the names of some oxyacids, okay? If you looked back at that table, I guess I'm not going to turn there, but you can turn to the table that has all these different kinds of polyatomic atoms that we're supposed to know. And here we have hydrogen phosphate. So this is this polyatomic with the hydrogen, phosphorus, and oxygen is called phosphate. So we're going to talk 8-ic. That was ic, right? So now we're going to change it to phosphoric acid. It was phosphate. And now we have, this is called sulfite, which is H2SO3, call it sulfite. That's the name of the polyatomic atom. ITE, we're going to call it sulfurous acid. We're going to change the ite to OUS. So here we have sulfate. So we have a sulfate. Usually these are all have to do with hydrogen, all to do with oxygen. So these are oxy acids. And so now we have sulfate, and then we're going to turn this 8 to sulfuric acid. So remember, 8 is ick. So now we have hydrochlorite. They call this hydrochloride. They're going to change ite to OUS. So hydrochlorite is going to be changed to, or hypochlorite is going to be changed to hypochlorous. Hypochlorous acid. Have you ever heard of that? Kind of a neat name. Hypochlorous acid. Now we have chlorate here, and that's going to turn to chloric. 8 is ick, and then ite is us. So we ate ick, and ite is us. So anyway, now we have perchlorate, another one, perchlorate, and now we have perchloric acid. So see how these are just polyatoms made out of oxygen here, and they have a name for them. And if it's an 8, you're going to turn. If it's 8, you're going to turn it to ick. If it's a ite, you're going to turn it to us. So OUS. So that is important. So I'm going to stop there and finish this up in the next video because it's getting kind of long here.